Welcome back to Neural Intel. Today we're diving deep into a really core question in machine learning. How well can neural networks actually learn when they get data continuously, like a constant stream?
Right.
We'll be unpacking some recent research focusing on the technical details, the nuts and bolts, and what it all implies about the fundamental limits and possibilities of this online learning process.
Exactly. We're stepping away from the usual picture, where you train a network once on some big data set and that's it. Think more dynamically. A network getting new information all the time, making predictions, finding out if it was right or wrong, and then adapting on the fly. Our goal here is really to dig into the math behind this, the theory, and see what the theoretical boundaries are, strictly the technical side based on the research.
Okay, so let's frame it. It's like a game, almost.
Get ready.
You have the learner, our network, and it keeps seeing new data points, one after another.
Right.
For each one, the network guesses the label, predicts, then it's told the actual label.
And if the guess was wrong, that's a mistake.
Exactly, a mistake. And what we're really zeroing in on is the total count of these mistakes over time. Researchers call it the mistake bound.
Yeah, it's a key metric.
Because it tells you something fundamental about how efficient this online learning can be, a really high mistake bound. That suggests it's inherently difficult, maybe impractical, to learn well in that online way.
And to really get a grip on the fundamentals, a lot of the theory starts with what's called the realizable setting.
Okay, what's that mean?
Basically, we assume, just for the sake of analysis initially, that there is some perfect neural network out there, one that could label every single data point correctly. Our learner is just trying to find it or get close to it through these mistakes and corrections.
Okay, so there's a right answer achievable by some network.
Exactly. There's also the agnostic case, where maybe no perfect network exists for the data, but starting with realizable helps us isolate the core learning limits.
Got it. So the network keeps adjusting, trying to hit this perfect target network. Now, you mentioned something earlier, and it seems central to the research. The idea of a margin.
Margin.
In simple terms, like how sure is a neuron about its decision? Can you break that down a bit more?
Sure. So imagine a single neuron trying to decide if an input is, say, category A or category B. A large margin means the internal calculation strongly points to one answer. It's a clear win for A or a clear win for B. No ambiguity.
Okay.
Small margin, that means it's close. The neuron's almost unsure, could go either way. And the research we're digging into puts a lot of weight on uno, gamma 1, which is the smallest margin found across all the neurons in the very first hidden layer of the network.
The first layer specifically.
Yes. And this OR1 value turns out to be really critical. It heavily influences how well and how fast the network can learn online. If those initial features extracted by the first layer are already well separated, with large margins, learning is easier.
Right, so getting clear signals early on helps a lot. Okay, this brings us to another term from the research, kind of technical sounding, the totally-separable packing number, or TSD.
Yeah, it's a bit of a mouthful. TSD.
What is that, and why is it important for understanding the technical limits here?
Okay, let's try an analogy. Imagine you have a d-dimensional space, like a big box. You want to pack points, or maybe marbles, inside this box.
Okay.
But there's a rule. For any two marbles you pick, you need to be able to draw a perfectly flat dividing surface, a hyperplane, between them. And this dividing surface has to have a certain minimum thickness or clearance around it that relates to our margin.
So a clear separation between any pair.
Exactly. And TSD is basically the answer too. What's the absolute maximum number of marbles you can pack into that d-dimensional box while satisfying this strict separation rule for every pair, maintaining that minimum margin on?
I see. So it's measuring how many distinct, clearly separable patterns can coexist in the data space, given a certain required margin.
Precisely. It's a geometric measure of the data's inherent complexity from a separability standpoint. And its value directly tells us how hard the online learning task is going to be.
Okay, that helps. So what's the punchline? How does this TSD connect to the mistake bound we talked about earlier?
This is the core result, really. It gives us both an upper and a lower limit on the mistakes.
Okay.
The upper bound says a good online algorithm shouldn't make many more mistakes than, roughly, TSD L1 divided by YEL squared, so TSD 112.
That's its ceiling.
Right. But then there's a lower bound too. It shows that for some networks and some sequences of data, any online learner is guaranteed to make at least around TSD plus 1e2 mistakes, especially if that initial margin May1 is bigger than some small value epsilon.
So you can't do better than that, fundamentally.
Pretty much.
Okay.
It means this TS number, combined with the margin, really nails down the inherent difficulty of online learning for these networks.
So let's think about the implications. If D, the dimension of the input data, is really large, which it often is, right? Images, text.
Yeah. Very often, yes.
And if this TSD number grows quickly with D, does that mean online learning could just become incredibly hard, maybe even blow up with too many mistakes in high dimensions?
That's exactly the concern. It points directly to the curse of dimensionality, potentially making online learning extremely challenging, maybe even infeasible for high-dimensional data. The number of mistakes could become enormous. But the good news is the research doesn't stop there. It also looks at scenarios where maybe this nasty dependence on D can be avoided or at least softened.
Okay, that sounds promising. How can we get around this dimensionality curse in online learning?
They highlight two main scenarios. The first one is called the multi-index model.
Multi-index model.
Yeah. Imagine your input data is massive high-dimensional D, but the actual output the network needs to predict only depends on, say, K-specific directions or features within that huge space. And K is much, much smaller than D.
Like, only a few things actually matter out of thousands of inputs. Exactly. It's like only a few dials on a giant control panel actually do anything. In that situation, the research shows the mistake bound improves significantly. It becomes roughly TSK 112.
Ah, so the D gets replaced by the much smaller K.
Right. And if K is small, this bound can even become polynomial in 1-1. That's a massive improvement compared to something potentially exponential in D. It means if the effective dimension of the problem is low, online learning can be much more practical.
That makes intuitive sense. Don't learn across dimensions that don't matter. Okay, what's the second way to potentially beat the curse?
The second route involves something called an extended margin assumption.
Extended margin, okay.
So remember how Bell 1 was about the margin in the first layer? Here, the assumption is stronger. We assume that every neuron in every layer of the network,
All of them?
yes, all of them,
Yeah.
classifies its own inputs with a margin up that's consistently bounded away from zero.
Yeah.
So good, confident decisions throughout the entire network depth.
Okay, so strong signals everywhere.
Pretty much. And if that holds, the mistake bound changes again. It becomes roughly log y. Here, L is the network depth, and y is the number of possible output labels.
Oh, okay. Log Y divided by gamma to the power of depth. That looks much better, especially the log part. No direct dependence on D or K there.
Right. It depends logarithmically on the number of outputs and polynomially on the inverse margin, 1 log, with the exponent related to the depth L. So if you can somehow guarantee these good margins everywhere, online learning efficiency gets a huge boost. The dependence on dimension is effectively removed.
That's really interesting. So either low effective dimension or strong margins everywhere can help, but there's usually a catch, right?
There is a practical one, yes. These amazing bounds we just discussed, they often rely on the learning algorithm knowing things like the margin og or that effective dimension hey beforehand.
Which it wouldn't in a real online scenario. The network just sees data. It doesn't get a cheat sheet about the data's properties.
Exactly. It has to learn in the dark, so to speak.
So how does the theory handle that? Learning without knowing these parameters.
Well, the research also explores adaptive learning. The idea is to design algorithms that don't need O or K given to them up front. They mention that algorithms exist which can achieve a mistake bound of roughly O-min M1, M2, 4.
Okay, wait. M1 and M2. Those are the bounds from the two scenarios we just talked about.
Yes, M1 is the bound from the multi-index model with K, and M2 is the bound from the extended margin model. The adaptive algorithm aims to achieve something close to the better of those two bounds, but raised to the power of 4.
Ah, so it tries to automatically adapt to whichever scenario fits best. Multi-index or extended margin. That's clever.
It is. It tries to get the best of both worlds without prior knowledge.
But that power of 4, that sounds like a potential hit in performance compared to knowing the parameters.
It is. That's the trade-off, currently. These adaptive methods often pay a polynomial price in the mistake bound for their flexibility. Finding adaptive algorithms that are more efficient, closer to the M1 or M2 bounds without that extra polynomial factor, is definitely an open research question. It's a known gap.
Okay, interesting. Now, another topic sometimes connected to network efficiency is pruning. removing connections or neurons to make networks smaller, faster. Does any of this online learning analysis connect to pruning?
Yeah, there's a neat connection. The analysis we've been discussing, especially around margins and the importance of certain directions, implicitly identifies a potentially small set of neurons or features that are really critical for the online learning process to work well.
The important ones.
Right. And if the theory helps us understand which neurons are crucial for adaptation, that directly informs pruning strategies. You'd want to keep those important neurons and perhaps prune away the ones that don't contribute much to handling new data effectively. It links the theory of learnability to practical network compression.
That's a cool link. Theory guiding practice. Okay, one last detail. Let's circle back to that TSD number, the totally separable packing number. How big can it actually get? You said it quantifies complexity.
Yeah, so there are known mathematical bounds on it. For AB, the margin less than or equal to 12, the lower bound is at least the maximum of 2 terms. One looks like constant AB and the other is just D.
Okay, that first termlet's exponential in D.
It is, and the upper bound is known to be, at most, another constant AB.
Also exponential in D.
Right. So the key takeaway from these bounds is that for small margins, meaning you demand very clear separation, TSD typically grows exponentially with the dimension D.
Which brings us back to the curse of dimensionality.
Exactly. It mathematically reinforces why high dimensions pose such a fundamental challenge for online learning, especially when you need high confidence. Large margin, meaning small epsilon in this context. The number of things the learner potentially needs to distinguish between just explodes.
Okay, let's try to wrap this up. What are the main takeaways for our listeners from this technical deep dive?
I think the big picture is that online learning for neural nets is deeply connected to geometry. Concepts like the margin, how clearly neurons make decisions, and this TS packing number, how many distinct patterns fit in the space, are fundamental.
Right.
The dimension D is a major factor, often making things exponentially harder. But there are escape routes. If the data has a hidden lower dimension, or if the network maintains strong margins everywhere, then efficient, even dimension-independent online learning becomes theoretically possible.
And we saw that adaptive algorithms try to achieve this without knowing K or GUP beforehand, though maybe with some performance cost currently.
Exactly. And this analysis also hints at which parts of a network might be most important, connecting to practical ideas like pruning.
Great summary. And true to the neural intel style, we've kept the focus squarely on these technical details and their implications. So, to leave you, our listeners, with something to think about. Given these theoretical challenges, particularly the curse of dimensionality, what kinds of new ideas, maybe in network architectures, maybe in learning algorithms themselves, might we need to develop to build AI systems that can truly learn continuously and robustly in the complex, high-dimensional real world?
That's the frontier, really. How do we bridge the gap between these theoretical possibilities and limitations and building systems that learn effectively over their entire lifetime? For anyone wanting the full mathematical rigor, the research paper itself is definitely worth exploring.
Absolutely. And as always, for more deep dives into AI and ML research, check out our webpage. You'll find the link in the description. Thanks for tuning in to Neural Intel.